So if we take a look at now our various trends, so for atomic radius, we can see in our graph here two things. We can see that as we go down a group, our atomic radius increases. We can see that as the ones in either the square boxes or the ones in the circles. As we go increase in atomic number, the values get higher. But we can also see across the period the values decrease. From the square boxes to the circles, we have a decrease across the period. So if we look at within a group, as we go down a period, the increased atomic radius makes sense because we're adding an energy level to place an electron in. And this additional atomic energy level is further from the nucleus, so therefore it has a larger distance, making the atom larger. But if we go across a period, what we notice is that we're adding electrons to the same energy level. But at the same time, my distance to that decreases slightly. Well, what we can see is that although I'm going across this period and adding electrons, I'm also adding more protons, with the number of core electrons remaining the same. So since there's more protons, I have a higher E and C value. And we know that force of attraction is E and C over d squared. D stays constant, E and C increases across the period. Since the E and C increases, my force of attraction is higher force of attraction. It means those valence electrons are pulled in a tiny bit more, and it means that they have a slightly smaller radius. What if we were to look at a ion radius for an atom? And so the radius of the ion that it forms. Well, we could compare that radius that the ion forms to two separate things. We could compare it to what it was itself before it became an ion, or we could compare it to other ions. So we can say in general, because a metal atom will lose an electron and it'll empty out their valence energy level, their atomic radius of the ion is smaller than the neutral atom. But a nonmetal atom, which gains an electron, it generally will be larger than its neutral atom. Okay. And the reason that my metal atom is smaller is I empty the valence. My nonmetal is larger because I have more repulsion occurring between those electrons in my valence energy level. Now, one of the things we have to note, or we can note, is that ions can be isoelectric with their noble gases. What this means is they have the same electron distribution. So if we take sodium here, and we look at neon, when sodium becomes an ion, it loses its one valence electron. And so now it has a full first energy level and a full second energy level. This is the same electron distribution as neon. So they would be said to be isoelectric. Likewise, fluorine would gain an electron to fill its valence energy level. So fluorine has the same electron distribution as ion, has the same as neon, with 2 in the first and 8 in the second. So as a result, we would say they're isoelectric. So we could compare the size of these three ions now. And what we could say is that metal ions would be smaller because they have a higher E and C. Right? And we know this because if we look at the E and C value of a neutral sodium atom, it has an E and C value of 1 because it's in group 1. But if we look at the sodium ion, when it loses the 1 electron in the valence energy level, it ends up having a new valence energy level. And so as a result, for the second energy level, which is now valence for the sodium ion, it only has 2 electrons in the core. And so, but the number of protons have not changed, so it has a higher E and C. And this higher E and C would be higher than the noble gas that it's isoelectric with. And so since it has a higher E and C, it's going to have a greater force of attraction. It's going to be smaller than the noble gas. Okay. and slightly less than a noble gas. What about in a nonmetal? Well, nonmetals gain. They have a decrease in their ENC because they have more electrons to attract. So they're going to experience a repulsion. So they're going to be slightly larger than a noble gas they're isoelectric with. And we can see this. This is, if we look at our noble gas, even if we don't change the ENC value, we'll see that its ENC is less than the noble gas. So its force of attraction would be less than the noble gas, so it would be larger. So therefore, if we look at them in terms of ENC, we would see that my metal ion or my cation would have the highest ENC to the noble gas as it's isoelectric with. The nonmetal ion would have the lowest ENC to the noble gas it's isoelectric with. Since they have the same distance to their valence electrons, the metal ion would be the smallest, the nonmetal ion would be the largest, noble gas would be in the middle. What about first ionization energy? Well, we know first ionization energy is the energy required to remove an electron. When we look at our trend, we can see that as we go down a group, and if we look at the squares, we can see our noble gases. Helium at the top of the group has the highest. Radon at the bottom of the group has the lowest. But we can also see that as I go across a period, it increases. And I can see lithium is much lower than neons as I go across the period. Remember, it always requires energy to remove an electron. The higher the force of attraction, the more energy required. So within a group, because we're increasing the distance to the valence electron, we're decreasing that force of attraction. And since the force of attraction is less, it requires less energy to remove an electron. Within a period, as we go from left to right, as we already said, my ENC increases while keeping my distance the same. Since the ENC is higher, the force of attraction is greater, and it requires more energy to remove an electron. Electron affinity. Now, electron affinity is the energy required to add an electron, or is the energy released when an electron is added. Okay, the trend is a bit more difficult to see. So one of the things that we have to do is we want to define our electron affinity, and we'll talk about this more in detail. But in general, it requires more energy or less energy is released as I go down a group. And so therefore, if we think about this, it means that to add an electron to hydrogen would not take a lot of energy, but it would take a lot of energy to add an electron to francium. So it becomes more positive. Okay. As we go across a period, it becomes less positive, meaning it requires less energy, or more negative, meaning it releases more energy. This is why it's important to define our electron affinity. So if I were to define it as the energy released, then I would say that lithium would, in my second period, would release the least. Fluorine would release the most when electrons are added. Okay, and again, this is because of my change in ENC while keeping distance constant, and so having a higher force of attraction. Okay, our electronegativity. Again, we can see with our squares at the top, we can see our noble gases. As we go down, our halogens, as we go down to halogens, we can see a decreased energy, but we can see as we go across the period, it increases. Okay. Well, as we go down a group, electronegativity becomes smaller. This is because it requires more energy. There's less force of attraction to the bonding electrons, which are further away from the nucleus, which means that I'll have a lower attraction. As I go across a period, it increases. Electrons are being added to the same energy level, same distance, increased ENC, higher force of attraction, easier it is to attract the electrons in the bond.